Thank you, everyone, for having me here tonight. My name is Brian Daly, Whiskey Bravo 7 Oscar Mike Lima. My daytime job, I work for AT&T. I'm an AT&T fellow. I also hold a number of positions in the ARRL amateur radio community. I'm part of the RF safety committee, also a field instructor and a technical specialist here in the state of Georgia. So what I'd like to do today is give a little overview of 5G to 6G and the evolution of cellular technology. So let's start with a bit of history going back in time. The first mobile telephone systems actually originated back in 1946. The Bell system first had its first mobile system in St. Louis, Missouri. And the first mobile calls in the car radio telephones actually started in 1946 when Motorola introduced the first equipment and partnered with Illinois Bell. Now, these were anything but mobile. Those first equipment weighed about 80 pounds. There were about 3 channels for all users in a metropolitan area. And that ultimately grew to about 25 VHF channels in the 154 megahertz bands. And they identified these by pairs of letters taken off the North American telephone dial at that time. So you got channel numbers like 55, 57, 95, 97, and so forth. These first systems required operator assistance in both directions. So you had to go through an operator, give the destination phone number of who you wanted to call, your phone number so they know who you were that were making the call, and an operator would actually patch you through. It wasn't until 1965 that we got the quote improved mobile telephone service. And this is when we got additional radio channels allowing for more simultaneous calls in each geographic area. We did have customer dialing that was introduced at that time, so we didn't have to have the manual calls set up by operators, and the size and weight of the equipment was reduced. Now, the interesting thing is that these systems were all based on single LAN transmitters, which had about 200, 250 watts, were normally high elevation, on top of a hilltop or high elevation building, used high gain antennas, and had about 20 to 25 mile coverage areas. And the problem with that is you got interference with other transmitters out to about 60 to 100 miles. Well, there had to be a better way to do that, especially if we wanted to have this in the mass marketplace. And today's cellular technology actually has its roots way back into the 1940s. The Bell system actually worked on cellular technology since 1947. And in 1979, there was actually a series of papers published in the Bell System Technical Journal, which described the Advanced Mobile Phone Service, or AMPS system. Now, what the cellular concept does, if you remember, those early systems had those single transmitters, high power, and interfered with other systems that were out to 60 to 100 miles away. Well, the idea in cellular is you want to locate the transmitter sites closer together and be able to reuse spectrum. And what these are those are the cells, those transmitter sites that are located closer together, where you can reuse that spectrum, is the basics of the cellular concept. Well, with that, you needed to do 2 things. You have to be able to locate, that is, what cell is going to be the best serving cell for your given location. And you need to be able to hand off, because if you're mobile, you're obviously going to be moving, and you had to be able to hand off from one cell to another. And there was also the concept of sectorization, where each voice channel in a cell is transmitted and received over one of the 320-degree sector antennas, rather than having an omnidirection cell. The net result of this is you want to increase the traffic capacity. That is, you want to put more mobile phones into a given area and be able to support that capacity with the system and allocated frequencies that you have. The FCC allocated the first frequency spectrum for cellular in 1974. And this actually looked at the eliminating of UHF TV channels 70 to 83, and also taking other pieces of spectrum between 806 and 947 megahertz. 40 megahertz of this spectrum was designated for the wireline common carrier use in the given geographic area, and then 30 megahertz was used for private services. And then an additional 115 megahertz was reserved pending further demonstrations at that time to prove the technology would be viable. In 1975, Illinois Bell filed a request to the FCC for authorization to install a test a development system in Chicago. That license was granted in 1977. And the first 1G cellular network was actually deployed in Japan in 1979. However, the US didn't see its first cellular system until 1983 in Chicago again, where the Bell system breakup actually delayed the deployment of the first cellular systems here in the US, where the assets from the Bell system were transferred to the regional Bell operating companies. So between 79 and 83, the Bell system breakup, that's what caused some of that delay. So I mentioned 1G as being that analog advanced mobile phone system, or AMPS. What a generation is, it's a set of standards defining the technological implementation of a particular system. So 1G was analog voice, and that's really all you got with that system. 2G introduced digital voice. It was known as digital amps, but there were other two competing technologies in the world. CDMA, which was introduced by Qualcomm and was one of the competing systems here in the US, along with digital amps, or IS-136. And over in Europe, they had the GSM system, or the Global System for Mobile Communications. So at the 2G timeframe, we had three competing major technologies vying for marketplace within the mobile world. Third generation brought us the smartphones. And again, we had multiple technologies. We had UMTS, which was the Universal Mobile Telephone System, which was a combination of GSM and DAMPS, and CDMA evolution to CDMA 2000. 4G is when the world came together and said, having multiple standards doesn't allow for interoperability between systems. And it was decided that there needed to be one system. So that's when LTE, or long-term evolution, as it was known, came into play. And 4G is also where we introduced IP, data, voice, and video. So everything went digital using IP connectivity. 5G, as you probably heard, is the most recent technology that's being deployed, and this brings about a continued advancement into enhanced mobile broadband, ultra reliable, low latency, and massive IoT. And we're going to talk a lot more about this in a few minutes, but this is just the basic introduction. And then the next technology after this is going to be 6G, and this will be in the 2030 timeframe. And as you see there, it's TBD. We still don't know everything that's going to be part of 6G yet. This graphically shows how all those technologies came together. So on the far left, we have 1G technology, which started out with amps. It moved to digital amps in the 2G technology, but we see the split into CDMA and GSM technologies. Those continued on evolutionary paths out to the 3G timeframe. And finally, it was decided in 4G, everything needed to come together. So at the bottom right, in that red circle, you see where the technologies really collapsed into one that now represents the global standard for mobile cellular communication, starting with LTE, moving through LTE Advanced Pro. Now we have the 5G new radio, and we're working on a technology called 5G Advanced, and this will continue now into 6G. Now, you'll also notice there's a Wi-Fi family in the middle, which is the WiMAX technology. that is still a technology that's evolving and will continue to evolve in the near future. So again, this just summarizes where we've been, and what the phones have looked like over that time frame. Obviously, the microelectronics has evolved along with other technologies, and starting with the big heavy phones, moving down now to the pocket smartphones that we probably all have. And again, starting at the far left at the analog voice, limited coverage, limited mobility, really focusing on voice only and not really any data services. At 2G, bringing in better voice, improved coverage and text messaging, and getting some data. But really 3G was the mobile data revolution, and that's what brought in the basic internet, multimedia, and smaller phones. And then finally, mobile broadband was introduced at 4G. So let's take a step back and talk about why standards are important. We want to make sure we have uniformity across producers so that we get a common set of requirements that we can support globally. As you're probably well aware, you can take your mobile phone and travel just about anywhere in the world. And as long as there's roaming agreements between your service provider and the service provider in the area that you're going, you'll have service. So we have the global interoperability, but also economies of scale. If we had to develop mobile devices only for the US, they would be extremely expensive to develop. Doing it on a global scale and having, billions of phones instead of hundreds of millions of phones, certainly brings down the cost overall. We have a common set of requirements and operational efficiencies, as well as being able to support the regulatory services that are required. When we look at global standards, there's really a hierarchy of standards, starting with international standards, which start up with the World Trade Organization, which defines the principles for standards. The three major international standards groups are ISO, IEC, and the ITU. There's regional standards organizations, which the main one here in the US for mobility standards is ARES, the Alliance for Telecommunications Industry Solutions. But there's also a number of other standards that are involved in the overall ecosystem. And then you have national standards that are used to develop specific country-based standards. And then there's a whole series of other groups that are developed to specific business markets. And one I want to point out in particular here is at the top of this chart is 3GPP, the third generation partnership project. This is the global initiative that develops the standards for all mobile cellular systems globally. So once we got to that LTE, that convergence at 4G, everything moved to this one standards group, and all standards from 4G to today are being developed within this partnership project. 3GPP is a partnership project of regional standards organizations across the globe. So ARES, as I mentioned earlier, is the partner of 3GPP here in the US. ETSI is the partner from Europe, CCSA from China, TSDSI from India, TTA from Korea, and Arab and TTC are two that represent the markets from Japan. There are also a number of other interactions with market partners and other standards organizations that all come into play in the development of cellular mobile technology. As we develop standards, there really is a three-stage development process. The first is developing requirements. Stage 2 is really the architecture, but there's other associated stage 2 work in security, in media, in operations and maintenance, and apps and mission critical services. And then stage 3 is the protocols and the coding that are being developed in order to support those architectures. And then on the far right side, you see the radio access network, which spans all stages. And each 3GPP has what's known as a release. And each release has stage 1, stage 2, and stage 3 built. Normal release timeframes are 18 to 24 months from the beginning of a release to the release freeze. And there's been a number of releases that we've had since the introduction of LTE technology. And I'll show you a chart in a few moments that shows where we are today. But I just wanted to show this, that a general release is made up of studies and work items for each stage, and really spans over that 18 to 24 month time period. So how do we get a generation defined? Well, the ITU-R, the radio sector of the ITU, develops a vision and technology trends for what they call the next international mobile telecommunications. And they focus on radio technology. For 3G, this was IMT 2000. 4G was known as IMT Advanced. 5G is IMT 2020. And 6G will be IMT 2030. Now, if you notice, there's a pattern there. And the pattern is about every 10 years, there's a new IMT. So IMT 2020 obviously is the 5G, and that was just completed in 2020. 4G, the IMT Advanced, was completed right around 2010. And the plan is for IMT 2030 to be completed around, for 6G to be completed around the 2030 timeframe. The ITU-R develops the technical performance requirements for each next IMT, and other groups outside of the ITU-R develop the specifications according to those technical performance requirements. And for mobile cellular, 3GPP is the specification setting group for that. Those specifications, as they're developed, they're submitted back into the ITU-R to be evaluated against the technical performance requirements. And if they meet the requirements, then they become an ITU-R IMT specification. Now, what's makes this important is the ITU is under the United Nations, and the ITU-R in particular follows treaties that are developed by various countries around the world in order to support the technologies that are being deployed. So that's how we get a global standard deployed, is through the ITU-R and through the United Nations. Various countries support treaties that say they will deploy technologies that the ITU develops. And as a result of that, we have global roaming today. So if we go back to IMT 2020, just historically, it actually started around 2014 is where the 5G IMT 2020 specifications were first started. And this started with the vision of the IMT beyond 2020, followed by the technical performance requirements. Those requirements were fed into 3GPP, who developed proposals for IMT 2020, and then they fed back into the ITU for evaluation against the requirements, and IMT 2020 specifications were developed after that, and we got 4G technology, or 5G technology, excuse me. So what did IMT 2020 get us? Well, it gave us three real main features. The first is enhanced mobile broadband. And what that means is greater than 10 gigabit per second peak data rates. The second is massive machine type communication. And what this is greater than 1 million devices per square kilometer. just to be able to support. And the third is ultra reliable low latency communication. And that is a less than 1 millisecond round trip delay on the radio interface. So what can that support? Well, if you look at enhanced mobile broadband, that means you're going to get faster speeds, the ability to do better streaming, online video, and services like that. Why would you want 1 million devices per square kilometer? Well, if you look at smart cities, you may have a lot of sensors deployed around a city. You may have a lot of IoT devices, Internet of Things devices. And finally, why do you need less than 1 millisecond latency? Well, if you're going to do self-driving cars or industrial automation or augmented or virtual reality, you need to have those low latency communications in order to support those features. The ITU actually has a document out called the minimum requirements for related to technical performance. And in here is specified all the requirements such as the peak data rate. And again, downlink peaks up to 20 gigabits, uplink peak data rates 10 gigabit per second. But that's not necessarily what you get from the user experience data rate. Peak data rate is when everything is perfect. You are, have full radio capacity. You have no interfering other devices in your area. But when you have a system that has other users on the system and you're not going to be able to achieve those peak data rates, what's the user experience data rate? And here you're going to get downlink user experience of 100 megabits per second and uplink at 50 megabits per second. Traffic capacity, we talked about, that's the total capacity within a geographic area. 10 megabits per second per square meter for an indoor hotspot is what the goal is. Latency, we talked about, 1 millisecond for the ultra reliable low latency. But for your mobile broadband experience, 4 millisecond latencies. And again, connection density of 1 million square devices per kilometer. Spectrum is also important. And for 5G, we're really talking about 2 spectrum categories. One is frequency range 1 or FR1, which is sub 7 gigahertz. And the other is frequency range 2 or millimeter wave, which is greater than 24 gigahertz. Now, the high band, there's spectrum that's being looked at in the 28 gigahertz, 24 gigahertz, upper 37, 39, and 47 gigahertz bands. But we also are adding additional millimeter band spectrum up to 70, 80, and 90 gigahertz bands. The mid-band spectrum is looking at 2.5, 3.5, the bands around the middle threes for mid-band. And then the low band spectrum, which is where you get your wider coverage. These are the traditional cellular bands and additional spectrum that's been allocated for 5G. And this is in the 600, 700, 800, 900 megahertz bands. In addition to that, there also is unlicensed, which is another important spectrum. So these are, typically what you would see for Wi-Fi, in your homes today. They're also looking at 5G hotspots, which not only in the 5.9 and 6 gigahertz, but also above 95 gigahertz. So there's a lot more spectrum that has been added to 5G and a lot more capabilities for even more spectrum as we move towards 6G. A 5G system basically consists of 3 components. You have the user equipment, which is the mobile device and a universal subscriber identity management or SIM card, a radio access network, which is also known as the NextG RAN. We have a G node B, where G stands for 5G and NB stands for node B. The node B is just the radio transmitter at the base station. And you can actually split a G node B into a central unit and distributed units, which give you some flexibility in deployments. And then there's the core network, which is known as the 5G core, 5GC, or the next gen core, NGC, which has both user plane functions, which handle the user data, as well as access and mobility functions that control access for the mobile device, and also the mobility functions such as handoff that's required for mobile devices. So there's a lot of fundamental trade-offs that we have to consider. And the first is spectrum versus hardware complexity. You know, if we have a lot of spectrum, we can have less complex hardware. If we have limited spectrum, we have to have more complex hardware. Well, in the cellular environment, obviously we've got limited spectrum. So that means the hardware is going to become more complex. And what do I mean by that? I mean the type of hardware to support OFDM, orthogonal frequency division multiplexing, which is how we modulate the digital signals across several different channels so we can reduce interference. We use a 5G new radio air interface, which is based off of OFDM principles. And we also use wider bandwidth technologies such as sub-6 gigahertz and millimeter wave. To achieve the goals of 5G, there's a number of different things we need to look at. Spectral efficiency. We have to be able to use the spectrum very efficiently because we have a lot of users and a limited amount of spectrum. So we have to look at incorporating massive MIMO arrays in order to do things like beamforming so that we can better control where we're going to direct our energy. Excuse me. We also have, you know, as we know, as we use these higher band frequencies, we're all very well aware that the propagation effects at higher frequencies is not what you see at the lower frequencies. I mentioned the traditional low band frequencies for cellular are used for wide area coverage because those signals, you know, propagate better. As we move up in frequency, we're going to get difficulties in propagating through buildings, difficulty in propagating great distances. We're going to have a lot of losses due to terrain, buildings, you name it. So we need to make the cell sites smaller and really densify the deployment of the cell sites so that we can use those higher frequencies and offset the propagation effects and the propagation losses that we're going to get at those higher frequencies by having smaller cell sites. Spectrum obviously is one of the main things that is the biggest factor for us as we move to 5G. We also want to look toward virtualizing networks and have cloud-based and software-based networks. And as mentioned, massive connectivity is something that needs to be planned for because, you know, when we're talking 1 million devices per square kilometer, that's really going to change the way we engineer and deploy networks. So, you know, just a very brief on OFDM. You know, the way this works is that we want to transmit the data on closely spaced narrowband subcarriers. So when we do the serial to parallel conversion of the digital signal coming in, when we do that inverse Fourier transform, we come out with a waveform that has each of these subcarriers such that they don't interfere with one another, so that the peak of one carrier is at the null of all the other subcarriers within there. And when you do this across all of them, it allows you to support more traffic within that particular bandwidth. We also have cyclic prefixes that we add to it. We need to maintain the ability to decode these narrowly, these space subcarriers, even on multipath fading conditions, which especially as we move up in frequency, we're going to get a lot of multipath because of the propagation effects at those higher frequencies. And also we want to do windowing to make sure we reduce any out of band emissions and keep the transmitted waveform within the spectrum that it's assigned to. The other thing to keep in mind is, we need to find ways to approach Shannon's limit. And now Shannon has developed the noisy channel coding theorem, which says that for any given degree of noise contamination of a communication channel, it's possible to communicate data nearly error-free up to a computable maximum rate through the channel, whether it be wired or wireless. So when we look at Shannon's theorem, the total data throughput or capacity of the system is dependent upon the spectrum that you have available, the number of antennas on uncorrelated signal paths, and the log of the 1 plus the signal to noise ratio of the communication channel. Well, with 5G, we have to figure out how we can tweak each of these numbers in order to get the capacity up to that maximum rate, or as close to it as we can get. What that means is we need more spectrum, we need more antennas, so we use MIMO techniques, and we use the higher order modulation schemes in order to get improve the data rates when the SNR is high. So all of these together combined allow us to reach us closer to the theoretical Shannon capacity of that channel. Now, how do we get more spectrum? As I mentioned, we've got spectrum all over the place, everything from the low band all the way up to the millimeter wave bands. In 5G, actually, this was started in 4G. We've introduced a capability known as carrier aggregation. And what this does is it's a method where we can make the device thinks the bandwidth is increased in order to increase the bit rates, and also helps extend the coverage and increase network capacity. So what we do is we aggregate 2 or more chunks of spectrum, and they don't have to be next to each other. They could be, separated by many megahertz. And we take these 2 and we aggregate them so they look like they're one contiguous chunk of spectrum. And this allows us to increase that W in Shannon's theorem so that it looks like it's a larger than it actually would be if we just use one of the chunks of spectrum alone. So carrier aggregation is a very important feature in order for us to get that up to Shannon's limit. Without that, if we only had to use the spectrum in the individual chunks, we'd come nowhere near it. So this is one of the methods we use to increase the spectrum or the apparent spectrum that's being used. There's also massive MIMO. Again, the millimeter allows us to use phase arrays that gives us much higher levels of spatial multiplexing. This also allows us to do beam forming, so that if using massive MIMO with beam forming, again, gives us those higher signal to noise ratios. So all those techniques combined, again, allow us to get more towards Shannon's limit and increase the bit rates over what we would normally get. So what do we get from 5G? How do we put this into the real world? Well, obviously, we already talked about faster downlink and uplink speeds. Well, that's going to give us a higher quality of service that's secure and reliable. Video actually is one of the highest uses of cellular technology today. So being able to have faster speeds with less lag, more bandwidth for video, as well as gaming, that's one of the important capabilities that 5G gets you. It also gives the ability for on-demand anything and everything. more immersive experiences. For example, many sports arenas today have deployed 5G technology, and you'll actually be able to have an immersive experience along with the real-time action on the field. You'll be able to get real-time information about what's happening on your mobile device. And also communications with vehicles, drones, and robots. That'll help enable safety and coordinated maneuvering applications, remote monitoring and failure of critical infrastructure, and real-time control for industrial and process automations within a factory. If the figure on the top right, there's three areas being looked at, as far as communication. The first is human to human, the second is human to machine, and the third is machine to machine. Under each of these, the three major categories of 5G are the extreme mobile broadband, massive scale communication or massive IoT, and ultra reliable low latency. And within each of those, you can see some of the potential use cases for each of those use cases. For example, the extreme mobile broadband for human to human will allow for video calling and virtual meetings. For human to machine, allow for fixed wireless and ultra high def video. And for machine to machine, would include video monitoring and mobile cloud computing. On the ultra reliable low latency service, human to human would include public safety mission critical services, vehicle to pedestrian services, vehicle to vehicle services, and so on. And in the bottom right, the massive IoT, there's many different areas that can be looked at there. There's agriculture and smart farming, transportation and logistics, such as fleet management, utilities, monitoring, smart meters, smart cities, smart buildings, consumers, industrial, and so forth. Some of the 5G vertical industries, I mentioned some of them already in manufacturing. This would include robots and automation, low latency wireless sensor capabilities, automated guided vehicles, tracking and monitoring of production. In the mining operation, this is 4G LTE technology has been used for several years, but adding 5G allows for innovative wearables and tools, sensors located on hard hats, body cams, and remote goggles, environmental sensors for early detection of dangerous chemicals, as well as automated haulage solutions, automated drilling solutions, and so forth. Utilities, this would include smart grid controls, computers, automation, new technologies, and equipment working with the electric grid. Healthcare and education. This has emerged, especially as a result of the COVID-19 pandemic. Telemedicine, telehealth visits, and remote patient monitoring became one of the prime use cases during the pandemic, as well as remote learning. And finally, gaming, the unique vertical that has high demands on wireless, both enhanced mobile broadband, as well as ultra low latency communications. In the automotive industry, this is one of the promising areas of 5G, looking at things like assisted driving, where we're talking things such as real-time maps for navigation, speed warnings, road hazards, and the whole goal is to reduce fatal accidents and traffic congestion. There's also autonomous driving, where the vehicle can sense its environment and navigate without or with minimal human input under all scenarios and conditions. In-vehicle media, where you could provide a multimedia connectivity to the vehicle and its passengers, including video streaming, virtual reality, augmented reality, and video conferencing. And finally, collision avoidance and related safety applications. Forward collision warning, emergency electronic brake lights, do not pass warning, left turn assist, intersection movement assist, blind spot warning and lane control warning, and emergency vehicle alerts. So going back to the standards, 3GPP, I mentioned, has a number of releases, and they develop according to releases. Release 15 and 16 were the first two 5G releases, and the whole goal of 15 and 16 were to develop the system that meets the IMT 2020 performance requirements, and also provide a path for early deployment of the 5G new radio without upgrading the core network. There were a number of capabilities introduced, including massive machine type communications, vehicle to everything communications, mission critical systems, and others that were introduced in release 15. Release 16 built on that and really brought in many of the system enhancements to support some of the capabilities that are being touted for 5G. Now, one of the things that came out about this is there wanted to be an early way to deploy 5G radio technology without having to upgrade the LTE network. And this is what came to be known as the non-standalone architecture. Essentially, what that means is you have your LTE network, but you have the ability to connect the 5G radio off the LTE network. Now, this isn't fully 5G. It gives you enhanced mobile broadband and some ultra low latency, but it doesn't give you all the capabilities that a 5G core network will give you. So you won't get the full set of security features that 5G will have to offer. And, and most of the other application services beyond faster speeds didn't come with the non-standalone architecture. The standalone architecture is what is the full 5G, and most cellular operators either have or are in the process of deploying standalone architecture today. And that gives you the full capability of 5G services. And, it includes the 5G core network as well as the 5G radio access network. In release 15, with consumers using about 11 gigabytes of data per month on their smartphone, the mobile broadband speed and capacity boost, relief from urban network congestion, and more home broadband choices are really what you see from release 15, especially with non-standalone. Release 16 brings in the enterprise and business applications. It also blurs the line between cellular and Wi-Fi so that you can use one technology between the home and outside the home. It also starts bringing in what's known as non-terrestrial radio access. And this is looking at initially satellite coverage, but eventually you'll also have airborne base stations in high altitude platforms. There's maritime aspects looking at ship-to-shore, ship-to-ship, and intra-ship communications, as well as various studies on a number of topics, including vehicle-to-everything, local area network support, wireless and wireline convergence, to name a few. Release 17 was just completed last year. And these continued the evolution of 5G services and bring the radio up to 71 gigahertz support, has industrial IoT, Internet of Things over non-terrestrial networks, satellite networks, the new radio over non-terrestrial networks, enhanced positioning, so you can actually get centimeter level positioning of mobile devices, a broadcast mode so that you can have broadcast and support broadcast services, non-public networks, which are supported inside factories, inside public schools, university campuses, things like that. Release 17 will also add improved battery health and power saving enhancements, in addition to the satellite access, support for uncrewed aerial systems, better known as drones, side link enhancements. Now, this is an interesting capability. So today, in order to communicate between cell devices, you have to go through the core network. You broadcast your signal up to a cell tower, and then it goes back into the network and routed to wherever it needs to go to. Sidelink is the capability for two mobile devices to talk to one another without a cellular network in place. It's basically turning your cell phone into the old walkie-talkie, where you can talk to another device that's near you directly. This was primarily added for public safety initially, but other applications such as two vehicles passing sensor information on a roadway is one of the other use cases for this, as well as drones and collision avoidance for drones. They're also looking at reduced capability devices. So if you have a low-cost Internet of Things device, let's say you're using it in an agricultural environment to monitor a field, you don't need all the capabilities of mobility management, because that device may not be moving. So there's capabilities that can be removed, and thus reduced capability devices are coming into play. I already mentioned operation extended to 71 gigahertz, new radio over non-terrestrial networks, and IoT over non-terrestrial networks, as well as coverage and positioning enhancements. If we look at some of the commercial activities such as agriculture, mining, and forestry, they're not going to be in the middle of cities where you have excellent cell coverage. So we need to look at ways to extend coverage using satellite networks and the ability to cover some of these very rural areas. And finally, enhanced support for non-public networks and proximity-based services, or what's known as sidelink. I mentioned non-terrestrial networks, and just a little focus on this. It's progressing to get the goal of integrating satellite systems with the terrestrial cellular network. And again, the whole goal is to provide coverage any place, anywhere. And we want to be able to use your traditional handset. We don't want you to have to buy a special handset in order to get satellite coverage. We want you to use the same handset that you would use day to day. And release 17 is introducing the specifications to support that in frequency range 1 bands, that's sub 7 gigahertz bands, in order to support satellite access. And there's a couple of different ways that are being looked at. One is your handset actually is the satellite terminal and communicates directly with the satellite using the same 5G new radio that it would have for the cell system. The other way is you would communicate with a cell site gateway that would then communicate to the satellite, and you would again, still you have your same device that would use, but the gateway would communicate with the satellite. Release 18 was just started and will be complete sometime in 2024. And there's a whole set of features that are being looked at for release 18, to the point where they're saying this is going to be called 5G advanced. So release 18, release 19 will have more capabilities for self-driving cars, industrial automation, smart cities, smart homes, cloud services, augmented reality, 3D video and ultra high definition screens, and looking at, again, in that gigabytes per second. And it's taking basically the features that have been developed in the initial 5G releases and extending those as we move forward in time. So switching gears here, what about 6G? 6G, as I mentioned, will be looked at around the 2030 timeframe. The ITU has already developed its report on new future technology trends, and they are working on their recommendations on a new IMT vision towards 2030 and beyond, which will be done later this year. The technical performance requirements will start development probably starting next year, and run till about 2026, at which time 3GPP will take those technical performance requirements, develop the technology specifications to resubmit back into the ITU as proposals for IMT 2030. That'll happen towards the end of the decade, with the evaluation occurring as we approach 2030 and the 2030 specifications coming out around early 2030. So what are some of the technology trends being looked at? Well, holographic communications is one that is really getting a lot of focus. There's a lot of work going on, especially in China, on holographic communication, and it's anticipated that as we get the speeds that we'll see, data rates that we'll see in 6G, that holographic communication will actually be something we can support. Tactile and haptic internet applications. So this would be supporting touch and feel across the internet, as I'd call it. So applications that would allow you to sense and provide sensing across the internet, much like you would as if you were touching something in the same room. We'll see network and computing convergence, extremely high rate data access and connectivity for everything, interactive immersive experiences with extended reality, multi-dimensional sensing, digital twin, where you'll actually have a twin of yourself or your applications that will exist in the digital realm, and be able to support a whole set of services based on that. Global seamless coverage through satellites and terrestrial integration. Artificial intelligence, especially on the air interfaces and in the radio networks. So controlling many of the mobility functions that we have today using AI. Spectrum as our scarce resource. We're going to have to figure out better ways to use spectrum, including sharing it with others. And that means sensing when spectrum is being used by others and not using the band and interfering with others. Moving, and spectrum from the very low bands up to the very high bands. And we're looking at terahertz frequencies for that. And, terahertz, the propagation is not going to give you citywide coverage. So what we're looking at terahertz for is mainly sensing applications, very close range sensing type functions. There's also a capability known as backscatter communications. Now, what this is, with IoT devices, one thing you want to do is to build those very cheap and have zero or low power. Backscatter communications essentially takes devices that don't have any RF front ends in them, and they use ambient RF energy to communicate. So if you think of the AirTags, the Apple AirTags today, it's similar to that, but taking it to the next level. So providing communications using ambient RF energy is one of the technologies that are being looked at as we move toward 6G. And finally, as we look toward quantum computing, one of the things we need to do is to be enhance trustworthiness of the systems. Quantum computing has the potential for breaking all the encryption that we have in place today. So we need to put quantum safe technologies in place as we move to 6G to enhance trustworthiness of the systems. 6G research is underway. The biggest group involved in North America research is the NextG Alliance under ARES, and HexaX is a group over in Europe, and the NGNM is an operator-led group that's also looking at defining operator requirements for 6G. The NextG Alliance has come out with 6, what they call their audacious goals for the 6G vision. trust, security, and resilience being one, digital world experience, cost-efficient solutions, distributed cloud and communication systems, AI native wireless networks, and sustainability. So these are the top priorities that are viewed as North America's contribution and leadership to 6G, and creating a leadership position for North America as we move towards 6G. Some of the potential use cases are, obviously we need to keep reducing cost per bit and simplify and provide simplified, energy efficient, and automated systems. We need to have end-to-end intelligent system automation, visibility, and traceability across the system with efficient management, targeting sustainable and flexible deployment and simplified operations. And we need to address traffic growth because it is increasing, exponentially. So we want to enhance human communication, machine communication, and enable services as we move towards 6G. So let me switch focus just a little bit here and talk about, some of the public safety aspects that we have with the technology. When 9/11 Commission report came out, one of the major areas that was highlighted was communications interoperability issues. And, in fact, there was the National Task Force on Interoperability came out in 2005, basically said, why can't we talk? Well, as a result of that, in 2012, Congress, through the Middle Class Tax Relief and Job Creation Act, created the FirstNet Authority. And this grew out of to address the 9/11 Commission recommendation calling for interoperable communications for all US first responders. The federal agency, the FirstNet Authority, was part of NTIA under the US Department of Commerce, and they were chartered to establish, operate, and maintain an interoperable public safety broadband network. And they were given 20 megahertz of spectrum for an LTE network in the 700 megahertz band. Now, what the figure on the right shows is, we started with a land mobile network, a commercial broadband network, and a public safety wireless broadband network. The whole goal of FirstNet was to converge the three into a single network that would be interoperable and support all the capabilities of those three networks. So mission critical push to talk are standards developed by 3GPP, and they defined a number of capabilities, including push to talk call handling, quality of service, authentication, security, interoperability, location services, and proximity services, which again is that walkie-talkie-like function that I mentioned before. They also supported not only voice calling, but also data and video calling services, which are defined by related standards. And the whole goal is to support mission critical over cellular to support FirstNet and other public safety applications. These critical communication features started in release 12 and continue to evolve and are evolving today in release 15 and beyond, to support device-to-device communications, group communications. So a group communication is basically, if you think of the land mobile network, it's a dispatch function where a dispatcher would communicate to all units that were within the network. That same capability was added to LTE cellular technology to provide that group type communication. Also mission critical push to talk, so that your LTE cell phone essentially became a push to talk mobile device. And that was extended to mission critical data and mission critical video as well. And now bringing that into the 5G realm with 5G mission critical push to talk video and data. There is also interworking between the LTE and existing land mobile radio systems. Those standards are being developed so so that you can have communication between the existing LMR system and FirstNet based systems. Priority access is another capability that exists on the FirstNet network. And you want to be able to have traffic priority for FirstNet responders over commercial and consumer traffic on the band 14, which is the 700 megahertz spectrum, without having to invoke wireless priority services. So first priority is always on for FirstNet subscribers, provides primary users with QoS priority and preemption capabilities, and they will not be throttled. So if there's congestion on the network, the FirstNet users won't be throttled back. They will get first priority to use the network. And there's top level incident priority that supersedes all other users on a temporary basis. FirstNet also has a number of deployables, cell on wings, flying cows, satellite cells on light trucks, microsat calls, communication vehicles, aerostats, and the whole purpose of these deployables are to make sure that we can bring service to where coverage is needed during any type of incident. Or if the cell network is damaged, say during a hurricane, we can quickly restore coverage to that area to provide service for first responders. And there are also a number of robotics that can also be used in order to support the public safety mission. So why do we care about this? Well, amateur radio operators may interact with public safety agency communications. So it's important that we have a knowledge of the agency communication systems. But more important, the 2012 Spectrum Act, which created FirstNet, also allows the spectrum to be shared with secondary responders, which are known as extended primary status, including amateur radio emergency service operators. So ARES members with FirstNet extended primary service can get priority network access and data prioritization, which will give them continuous data priority across voice and data. And they can be uplifted to primary users, which will give them even higher priority levels and preemption capabilities. And this works both not only on the LTE band 14 700 megahertz FirstNet band, but also it's across all of the AT&T commercial bands. So you get the priority and preemption capabilities on any band, and it applies to both voice and data. And also FirstNet Assist, with that app, you can actually view all mission mutual aid events within your proximity and request elevated priority access for that incident. So amateur radio operators supporting ARES teams can actually go through a process to obtain FirstNet service. You would need to get a letter authorizing you to obtain the subscription that you're supporting an ARES team or an agency. And once you have a letter that gives you authorization, you can contact an AT&T FirstNet Solutions consultant and request FirstNet to be added to your subscription. It does require a FirstNet capable device on AT&T service because AT&T is the operator that runs FirstNet. But if you have that, you can obtain a FirstNet Black SIM and add the subscription to your account, and that will give you the priority and preemption capabilities of FirstNet, and it'll also give you access to the FirstNet App Store. So with that, I think I ran a little bit over, Dan, but let me open it up to see if we have any questions.
Okay, if you want to lower your desktop, and we'll see what we got here. Okay, we got Dan, WL7C. Oh, go ahead.
So am I given to understand that I can write a letter on ARRL ARES letterhead and give that to somebody, and they can take that and they're suddenly magically eligible for FirstNet? And that's just sort of a lead into the real question is, how does the pricing of FirstNet compare to just commercial pricing?
Yeah, your first question is essentially yes. I mean, there has to be some level of coordination with your local ARES leadership and approval by your ARES leadership to say, yes, this is really supporting an ARES mission. And once you have that, and you know, it's an authentic letter and you are supporting it and can attest to the fact that you're supporting an ARES mission, yes, you can get FirstNet service.
Somehow, okay. And
here in
let's say, what's the financial incentive for me as a amateur radio service licensee to do that?
Well, the incentive is you would get the FirstNet services. Now, obviously, it's going to be out-of-pocket cost to you as an amateur radio operator, because your served agency is probably not going to pick up the cost, which I think is somewhere in the $20-something per month to add the service to your existing account.
Okay, fair enough. I'm full disclosure, I used to represent a federal agency in negotiations with communications companies.
Got it. Yeah. We recently started this here in Georgia. We're actually managing it through this section emergency coordinator who signs off for any ARES team member that wants to go through the process and add it to their account.
Well, I don't have one hanging nearby, but I've got one of those badges that says I'm one of them.
Gotcha.
Okay, Steve, you want to take it?
Yeah, I just had another question here about all of this. Is this exclusively the 501c3 amateur radio emergency service by the ARRL, or would the GEMA, the Georgia Emergency Management Agency, has a government-sponsored organization that is the OXCOM program from DHS, CISA, ECD,
Right.
And I just wondered, do those individuals also, what do they need to do in order to obtain the FirstNet? And my question, I guess, is, as a volunteer resource, does the ARES individual have to get signed off on by an authority having jurisdiction or a critical infrastructure partner? Just as an individual with ARES, wouldn't the letter have to come from an authority having jurisdiction or one of the critical infrastructure partners that he is associated, or she is associated with?
Well, here in Georgia, the way it works is, as I mentioned, it's the section emergency coordinator manages it, and basically there's a coordinator under the SEC that works with the FirstNet authority and essentially says, yes, these people have been vetted, they are ARES members for Georgia ARES, and thus they're authorized to obtain FirstNet service under our umbrella.
Okay, the reason why I asked that question is that the Georgia Emergency Management Agency recognizes the OXCOM program,
Right.
not the ARES program.
Yeah.
The ARES program is a component of OXCOM, but it's not the program.
Right, right. Yeah, it's specifically the ARES program that's given the authority. And I know others in other states have also obtained FirstNet service just by ARES affiliation and getting a letter that authorized them, states that they're part of the ARES mission. They don't have to be affiliated with any critical infrastructure partner necessarily, but they have to be part of an ARES program that supports an agency. And it could be your local sheriff, it could be.
Okay, there you go. All right, I see. So does who provides the certification or the proof that they are supporting an agency?
So here in my local county, my EC signed off on it and provided the name to our SEC, who then provided it to FirstNet.
Okay, I see. What county are you in?
Forsyth in Georgia.
Are you anywhere near Fulton?
Yes.
Okay. Well, thank you.
Yeah, thanks. And Steve, if you have any questions, my call at arl.net will work if you want to dive into it further.
Okay. I'll be in Atlanta Tuesday through the 18th to the 21st in a FEMA Region 4
Right.
planning, and I want to address that there.
I may be down for part of that. I'll see if we can connect.
Sure. Thank you. Appreciate it.
Uh-huh.
Okay, let's take one more, then we'll go over to the chat things. Go ahead, Jim, take it away.
Two questions. Who provides the authority to move up to establish the FirstNet priority? I think you mentioned that it's not always there. It has to be done per incident. So who provides that? And secondly, I'm seeing some boxes up on light poles around my neighborhood. Is that 5G?
Probably 5G, because again, with the densification, especially as we get up into the gigahertz range, where we are densifying and providing some of those dense cell sites, or could be even fixed wireless into the home. So yes. The first question, any FirstNet user has priority and preemption capabilities. There's different levels. For example, if you're at the top of the chart, you basically can preempt and have priority over everyone, and it moves down from there. This extended priority levels that ARES members would get are pretty well at the bottom, but you can be bumped up by your local agency if you're supporting an event and that agency says, we need these amateur radios operators who have FirstNet devices to be at a higher priority. You can get temporarily moved up.
Okay. Dan, you got your hand up again.
Yeah, so are there specific coverage maps that indicate where this is available and where it's not?
Yeah, in fact, each state, I think, has a map on a website. If you go to firstnet.gov, look up your state. Typically, each state would show a map of the coverage area for your state.
Okie doke. Thank you. And how do I say it? The description of the standards evolution process was fascinating and multifaceted. And it didn't remind me at all of anything that I'm reading on a daily basis that's put out on the vulnerability lists that CISA publishes.
Yeah.
For communications, and it's way more than communications. You pointed that out. It's life in America as we know it today.
Right, right.
And I'm just kind of curious about, is there any government input to these standards to how this came about? That what is it, 3 PP.
3GPP. No,
Yeah.
actually, that was all industry driven. The government gets involved in the ITU process because that is a treaty organization. So the State Department is heavily involved in there. But 3GPP itself is all driven by industry.
Okay, and I'm really curious about the levels of LTE 4 or 5 you have to have for PTT emergency communications to really be viable. You know, it sounds like an ideal that is always going to be just beyond reach for a fair amount of the country.
Actually, it's not. If you look at push-to-talk capabilities for FirstNet devices, I mean, that's pretty well nationwide today. And again, that you asked about the coverage, it actually probably extends beyond the commercial areas because there's a lot of rural areas that we need to have FirstNet coverage, public safety coverage. So it's actually there. Push to talk works. There are push to talk applications that are in play today for FirstNet devices.
Okay,
Thanks a lot. Yeah, it was a great presentation, and it's more in depth about what FirstNet is aspiring to, I should say.
Yeah.
definitely opens some eyes to what FirstNet is. Okay, do you see the chat session there?
I do. Yeah, I see Carl in Seattle. Yeah, $52 a month. He says, again, I think a lot depends where you are, what service you have, base service. So yeah, don't hold me to any dollars. I'm technologist, not a salesman. So okay, listen, that capacity was 3% of available phones. How does capacity change? Today, cellular networks run what we call hot. They're almost at full capacity 24/7, 365. So with that much streaming, you know, that's why we had to come up with creative ways to get more frequency bands, do carrier aggregation to have more bits per second supported. And again, as you mentioned, it becomes critical during a catastrophe. You know, if you find any major event, the one thing you hear is, well, the cell phones didn't work because the network was congested. That's because we've got so much data running on the network. There's really not a whole lot of spare capacity in the network. That's why we have the congestion, and that's why, you know, not to sell FirstNet, but that's one of the benefits of having ARES being able to be part of FirstNet is you get that priority preemption plus access to band 14 at 700 megahertz, which allows you to overcome that capacity crunch during disasters. Does radio amateur spectrum interfere? No, because the ARRL has done a good job at protecting the amateur bands from us in the cellular network. Yeah, so certainly, you know, there's no interference because of the strict rules in place on out-of-band emissions and interference that we have. And like I said, ARRL has done a good job at making sure that the amateur radio spectrum is protected. Oh, except for 3456 megahertz. Yes, Dennis. I think somebody had let's see. Carl in Seattle had a comment.
One other comment real quickly, Brian, and hello, haven't talked to you for quite a while.
Been a while, yes.
During the Oregon wildfires a couple of years ago, AT&T brought in FirstNet capability to this region that had lost everything, all communications. And what several people discovered, and it's worth noting for your audience. What was brought in for FirstNet only worked for FirstNet if you had a FirstNet SIM. It did not work on a regular AT&T account. So
Right,
just
right.
because AT&T responded and set up cows and colts and blah, 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 it only supported FirstNet subscribers.
Yeah, good point, Carl. Yeah, this next question, would we be here today if the Bell system had been left intact, or would the rollout be slower? Put another way, was the Bell system moving at the speed of light? That's an interesting thought question. On one hand, the competition has advanced the technology quickly, but on the other hand, it brings so many more players in, it makes the standards process very complex and in some aspects contentious. Whereas if you had just the Bell system in place driving it, would it have been quicker? Good question. Yeah, I think there's pros and cons either way, and hard to say. Gets and WPS, yeah, these are valuable programs that do offer priority to access to first responders. And how do we ensure the same priority is available quickly to involving satellite? That's going to be an interesting thing. Yeah, certainly we need to be able to, you know, if we're going to rely on non-terrestrial networks for some of these critical communications, if those systems also support both public safety as well as commercial systems, there needs to be something like a priority service implemented so that they could have that communication link available in the event of a disaster. And I agree. I think it's something that needs to be thought about, possibly legislated before the systems come on board. I haven't been following too much the interference with radio altimeters. I know there's been an agreement made between the major operators and the FAA. For those who aren't aware of this, some of the older radio altimeters in airliners that are used for approaches into airports, there was interference concerns with the cellular bands around those frequencies that were used. And a lot of work has been going on the past couple of years to try to mitigate that without having to replace altimeters in I don't know how many airplanes. I know there's an agreement that's been made between the operators and the FAA on making sure that interference is mitigated by how deployments can be made of those frequency bands in what proximities around airports. But I don't have, I wasn't directly involved in that, and I don't have the full background on that. Hardening cell sites, yeah, I think that's, you know, certainly wildfires, earthquakes, you know, any type of event, you know, that's one area that is always being looked at, is how can systems be hardened. Another area we're looking at obviously is EMP, which is, you know, what will be the effects on networks from EMP. And especially near Earth orbit satellites, so they don't get shot down by the Air Force. I think that was the end of the questions that I saw.
Me too. I don't see anything more there. It's been a long one, but a darn good one. Appreciate you doing this.
You're certainly welcome.
Okay, open it up. Any comments, folks? Any anything at all? Okay.
Oh, we got another message come in. Nope, that's it. Okay.
Okay. Okay, well, with that in mind, I'm going to close this down. Again, Brian, I appreciate this very much. It's very, what it did was bring out more questions that Okay, so I'm going to close it down, 73s, and I'll see everybody next week.